Okay, yeah, so now that you've already been through like 6 different presentations, I'm gonna hit you with yet another one and present like the first model that you're actually going to use in most of your tasks as a simple baseline. So we're going to talk about regression and in particular linear regression. So the main idea, the main motivation behind this is that this is kind of for many problems, it's the first model we will try, and it's basically a model that will help you use historical data that you might have, so something that you have recorded about whatever problem you want to tackle, to make predictions for something else. So then linear regression in particular is one of the simplest models you can learn, and this is why it's one of the ones you use for a baseline. So I'm going to start by explaining first what is this thing called regression, like the problem. Then I'm going to explain simple linear regression models, multiple linear regression models, which are not that harder than the simple ones. The closed form solution for this, just going a little bit over that. You don't need to know that into detail. Then we're going to finally learn how to use this inside the scikit-learn, which is what you'll mostly use. Some pros and cons, and then in the end I'm going to introduce something that you'll learn better in the next unit, which is gradient descent, in particular for linear regression. Yeah, so what is a regression? So you might kind of divide the problems of doing predictions into 2 different classes, and the first one, which is on your left, you can think of it as having data that's either you want to classify as either as A or B, like as being, I don't know, you have a bunch of pictures and you want to know if there's a dog there or not. So like class A would be there's a dog, class B would be there's not a dog. And that's classification problems. You'll learn more about them in the next unit. And then you have regression. In regression, you don't have classes. And what you want to do is you have a bunch of features, which is like some data you observed, some data, like some experimental data even, and you want to just like predict some targets. And this might be, for example, house prices. You have a bunch of factors about your house, so you know the size of the house, you know the area of the house, like where it's located, you know a bunch of things about that house. You have some historical data on how that affects prices, and you just use regression to like predict a specific value. And this value is a value in a continuous range of values. And this is what we call a regression. So normally, like the most common example would be like your random dots that seem like a line, and you just plot a line across them, and that's doing a regression. So that line would represent what your predictions would be for your targets. And this is what we're going to talk about. So there's 2 important concepts here. You have like what we call the independent variables. These are basically your features. So you can like gather a bunch of different features. This would be like the location of your house, the size of your house, is the area polluted or not, a bunch of different things that you just gather. And this is what we call features. And we consider them as independent variables, so they don't affect each other, supposedly. This is one of the assumptions of regression. And then you have the dependent variable, and this is basically what you're predicting, and what you're assuming depends on your other variables. Yeah, so some examples of this, like I said, is the house pricing thing. You want to predict like what a certain house will cost given the data that you already have. Or for example, Uber rides. Imagine that you have a bunch of data saying that in every specific location, a ride of a certain, like with a number of kilometers, takes a number of time, like a given number of minutes. And you might want to use this data to just predict your next ride, how much time it will take. So you have a bunch of other examples. You may want to predict sales, for example. You may want to predict economic stuff. There's a bunch of things where you can apply regression as a very basic model. So going a little bit into simple linear regression, so you can imagine the linear regression as having multiple features, and simple linear regression is a very special case where you have only one feature. And so basically this is very easily represented with this expression. So we normally add a value which is called the intercept. Basically, if your input is 0, this is what your regression will output, and we have an input and a coefficient associated to this input. And this is like what we call a linear model, because the prediction is basically just a linear combination of your features and your coefficients. Yeah, and there's a very simple way of putting this into code. That's one of the ways. So you might have this vector of weights, and you use the first weight as your intercept and the second one as your coefficient, and you get your prediction. It's super simple. Anyone could implement this. And this is kind of like what I was telling you about. So this is the usual visualization. You have your data scattered, it looks like a line, so you put a line on top of it. And the thing here is, so the meaning of these two, the coefficient and the intercept, you probably know this from like very simple math classes that you've probably had in school. So if you vary your slope, it means that you either, so for example here, for each, this, I don't know if you can see from like far away, but the x-axis is change in unemployment rate and the y-axis is GDP. So the more unemployment rate you have, the more the GDP drops. And this is basically at each unit, it will drop by a certain amount, which is your slope. So you can like make this slope more steep or less steep, and this will fit better or worse your data, right? But how do you see like, just how do you get a sense of how it is in fact fitting the data? So you can think, okay, I'm looking at the line, I know it looks well, right? But if you just tilt it a little bit, is it better or worse? Can you tell, like, would this be better if it was steeper? Would it be worse? We don't know, right? Because we can visually say this and up until a certain point, right? If I just like completely make the line opposite, so growing larger as the unemployment rate goes larger, you know that this doesn't fit. But if I just tilt it a little bit or put it slightly up or slightly down, you have no idea. So how do we evaluate our model? We rely on, sorry, that text should appear earlier. we rely on what we call our errors, and our errors would be how good we predict each of those single points, right? So you have those points, you know their labels, you know which values they should match, and we have our predictions from our model. So basically the values of that line. And you just if you do the difference between them, you can call that your error, and we can do a bunch of metrics over that error. For now, we're going to use the mean squared error, which is this one that's presented here, but there's others that you can use. The thing that you need to know is that this is, like you can see, proportional to this difference. So the higher this difference, the bigger your error will be, and so the worse is your model, right? This is all pretty simple. And this is kind of a visualization of that. So this distance between the prediction your model does and the data that you had is what you want to minimize in some way. So we can see that clearly the line in the left is much better and it has much smaller errors there. So, and what is multiple linear regression? Why are we splitting these two cases? So the simple linear regression is very easy to visualize, right? You have that chart, it's just a line. When you get to a multiple linear regression, you basically have multiple features, multiple inputs that might affect your target differently. And the visualization starts to get a little bit more complicated, right? So if you have just two different features, you will get something like this. You can still visualize it because we can still visualize this kind of 3D stuff. You'll have a plane that will basically represent your model. But over than that, we stop being able to see how these models look like, right? So it's much harder to visualize. So the simple linear model is a very good way to start and to get like a visual sense and like an intuition of how these things work. So yeah, basically the multiple linear regression is just like a fancy name for the same thing as the simple linear regression. It just has multiple inputs, but all of them behave in more or less the same way. And you could write it in the same way as before, just like an enrolled expression with all your inputs and coefficients. And here you have like an example with 5, but you can also imagine that as these inputs grow larger, it gets a bit hard if you just like write everything enrolled, right? So we can also collapse, and this is normally the way, and what you will see in the notebooks, the way of representing this notation, where you collapse all your sums of features and coefficients in this neat expression. And then you expand it to whatever number of features you might have, either 5 or 1,000 that wouldn't fit in the enrolled expression, or even more, like 1,000,000 features. And so this has the same, exactly the same meaning as the expression on the simple linear model that you've seen before. And additionally, it also has a very simple way of implementing it in code. So you can still implement this in a one-liner in your Jupyter notebooks. So again, how do we evaluate this model? If you think about it, like we increased the number of features, but we didn't increase our targets, right? So our target is still the same. We're still trying to predict one single value, and our model will still output one single value. So in the end, we have exactly the same error measure that we would have for the simple linear model. So we can reuse the exact same metric here, and that's exactly what we'll do. So in terms of error metric, you'll be using this one for like the whole unit. Tomorrow, you'll learn more about other possible metrics that you might use. Yeah, and now I'm going to try to like just give you a little bit of an overview of how do you get to a solution of this model? So, okay, you know that you have to fit a line, but you don't want to be, even if you have the error measure, you don't want to be manually tilting the line to see when the error is decreasing and when the error is increasing, right? So we want a programmatically way of computing this. And so the intuition, one of the intuitions for this is we want to minimize our error, right? That's exactly what we want for any model. So if you draw your error function and it has this neat form where you just have one single minimum, which is the perfect situation, we want to know how to get to that minimum, right? To that place where the error value is as low as possible. And for this, we use what we call gradients. So the gradient basically gives you the rate at which your function changes. So when this is very high, this is bad. When this is as low as possible, we're in the minimum spot. And this is typically when this gradient is 0. So this is kind of the initial idea that leads us to a solution. You don't have to know anything about how to compute gradients or derivatives. Nobody's going to ask you that. Everything is a given. So you just imagine that you have a function that allows you to get this value. So you know at what rate your function is varying, so you can try to get to 0. This is just for whoever is more curious to know how these expressions look like. And you have a particular notebook that explains you how to get there. But in the end, for the simple linear model, this basically translates to these two expressions. So you can compute your coefficient just by getting the covariance of your inputs and your labels over the variance of your initial input. And you can compute the intercept just with the coefficient. So this is all very simple, and it's basically what you're seeing here. It's what scikit-learn will eventually output also. So it's what it implements behind it. The closed form solution, and it helps if you know have some concept of matrix notation, but obviously we're not going into detail there. It's also represented in a one-liner. It's very simple also. So either of these, you can basically replicate whatever scikit-learn will output then. Now there's a really important thing here, which is when you're doing multiple linear regressions and you have a lot of variables, the assumption of independence is a really important one. So we don't want our features to be correlated. We don't want our features to mean the same thing. So if you give it, I don't know, the size of if you give as a feature the size of your house, but if you give as a feature also the size of your living room, you're just basically, in a way, repeating features, right? Because they're bound to correlate, or the number of divisions, or something like that. So, and multicollinearity, which is what we call when two of these features are very, very correlated, is something that we don't want at all, and will reduce a lot the precision of the estimated coefficients. So in these things, it's important to know kind of which features you are using and all that. So now let's get to actually the part that you will probably find more useful, which is the coding part. And scikit-learn offers us, offers us a module on regression, and it has the linear regression implemented. Both this closed form solution, which is what we're going a bit more deep into, which is the linear regression, but also the SGD, which I'm just going to go over in the end. And you can basically use some of these data sets to test it out. So one of these examples is exactly the housing situation that we looked at. So you can download this data set and just see, for example, a bunch of features that are affecting. You have, for example, the age, which should be very simple for you to understand. You have the NOx, for example, is the pollution ratio. You have a bunch of features here. And in the end, you have the median value of the owner-occupied home, so a price. And this is what you want to predict. And to predict that price, you can basically just fit this model, which is the linear regression class. And in the background, it will be doing all those computations that you don't really want to know about. And so basically, you're just giving it all your features, this X that you're seeing there in fit, and all your labels. And the model will do all of these calculations behind, and it will lead you to the line with the lowest possible error, which is what we want in the end. And so after this model in scikit-learn has a bunch of functionalities. So it also allows you to give more data to predict the next labels. It allows you to produce a score, which is another metric that you will learn about later in the SLU07. So you can also compare, for example, different models using these scores. So it has a bunch of useful stuff. And it's literally 3 lines, right? So another important thing to understand when you use these models is you're basically trying to output your coefficients, right? You have your inputs and you want to know what are those values that are going to multiply that are going to lead you to the best possible predictions. And when you're loading any data set, you will see that, and we can see in the initial table, that all of the different features have kind of different scales, right? So we have stuff that is around like 60, 70, and very high values, even 300 or 400. And then you have stuff that is really small, like 0.4, 0.5. So clearly there's a huge difference in scale on your features, right? So if you just compute the coefficients on top of this, you will get that apparently the pollution is the most important score that you can have when computing house prices. So apparently, and this is in particular a data set from the Boston houses. So in particular, you would assume that people in Boston really hate pollution, right? Because like this is, the houses are much more expensive if they're in an area without pollution. But actually, this is the problem with the scale of the values that I was just talking about. So if you actually normalize all your values to be in the same scale, we will see differently. So this example here loads a normalized version. It runs exactly the same commands, and then the coefficients you get are completely different and reordered, right? So now the pollution is actually not even in the top 5 most important coefficients. And so this would be the other ones would be the major drivers for actually the house pricing in the house prices in Boston. Sorry. In this scenario. Yeah.
How did you normalize the features?
You basically pre-process the features. So you have like, imagine that you have features that go from 0 to 400 and features that go from 0 to 1. So you just want to, given so how wide they spread, you can just kind of collapse them to the same scale. There's ways to doing it. I don't want to go a lot into the mathematical details, but you can just use that and just kind of scale them down so they fit exactly the same thing. So you would scale down, for example, what would be your 400 would turn into 1, and what would be your minimum would turn into 0 or something like that.
An additional factor,
yeah, you can basically, as long as in the end, you know, basically the easiest way I think to understand is that, so whatever maximum you have will turn into kind of the maximum of your new range, whatever minimum to the minimum of your new range. And in the end, you will have like both the pollution rates and both the, I don't remember what the other one was, but let's say the area or whatever, ranging from 0 to 1. It stops having the same meaning, right? Because you don't know how to interpret the location from 0 to 1 or the area from 0 to 1. But when you feed it to your model, you'll have much more reliable results in this regard. So when we use this same scale, we are much more able to, like, just looking at the coefficients, understand which feature will be more relevant or not to this model. And in this particular regard, if you want to also normalize like these coefficients from 0 to 1, you can use this expression, and you can see from this that over 50% of the feature strength. So the feature strength, if you sum these all to 1, you will have your 100%, right? And just the top 5, I think these are 5, the top 5 features have more than 50%, right? So these are actually the ones that you should focus on, probably. So this is also an important way of interpreting the linear regression that you have, in particular when you have like a lot of different features like in your multiple linear model. So instead of 11, you can have like thousands and thousands. And maybe some of these features are not as important. But you'll also see like how to filter these features and understanding better their weighing in the models a bit later on in other learning units. So yeah, basically feature scale really, really matters. And the importance of the feature, you can kind of relate to the coefficient that it has. So if your model is giving like a weight of 5 to one feature, it's obviously much more important than a weight of 0.5 to another one. And these are the two main things that you can take kind of out of this computation of the coefficients and this normalization of your features. So some pros and cons of linear regression is that, well, it's really easy to understand, like, and especially the simple linear model case where everyone can kind of imagine that line over over your data and see how it fits or not. It has a fast optimization, so it's very fast to compute, and it has some extensions available to deal with some like weird cases, outliers, sparse data, and whatnot that we're not going to go into detail. But there are extensions to this model that cope with all of this. Some cons is basically the assumptions that we did. So you have to have like independent features or almost independent features. So if you don't know anything about your features and are just trying to feed random data, you might end up with really, really bad results. And this is not good. So it's not something that you can use if you don't know kind of the meaning of your features, or at least if they are somewhat correlated or not. So this is an important thing to keep in mind, especially if you're trying this baseline on a problem that you don't understand that well, that this might not be the best possible fit for that problem. So, and also like when you have categorical features, so imagine a feature might be categorical if it only has a few values. So instead of like the area, which is also a continuous value, you might have just if the location might be categorical. So is it in Lisbon? Is it in Porto? Is it in some other place? Is it in London or Boston? And these might be tricky dealing with linear regression when you have basically a number of different values, and some of these values are very few occurrences. So this is also can be a con to this particular model. So you need to be careful with these things when you use linear regression. So just to finalize this and give you an idea of other things that exist that also tackle linear regression. So we talked about basically the closed form solution as implemented by scikit-learn. Gradient descending tries to solve exactly the same problem. So we're still in the same scenario. We want to get to our lowest possible error, but it does so in a different way. So instead of trying to solve an optimization problem and get the minimum like with some math, it basically does so iteratively. So basically it uses this gradient. It knows that the gradient, okay, if my gradient is going up, then I'm increasing the error like at a very high speed. If my gradient is going down, then it means that it's changing less. So I'm in a better part of this function, right? And we still want to get to the gradient of 0. So what we do is basically just use this value and go in the opposite direction, right? We don't want the error to increase, so we just go in the opposite direction of this gradient. And we can take small steps in doing so to slowly descend across this function, kind of as that image tries to convey. And this is a much more simple rule. So comparing with the other thing that you saw earlier, it still has the derivative here, but you can picture this as some function that somebody gave you and that you trust is right. And you just update your like coefficients with some weight that accounts for the derivative, and it goes in the opposite direction. So this is a very, very simple rule. And it also has a very, very simple implementation that I'm not going to explain in detail, but you can see it's also like just 4 or 5 lines, at least in this very simple scenario. So this is a very powerful method, not only because it can be applied to other types of problems, so it's not exclusive to this particular problem, but also because it's very simple to understand what it's doing when you're basically just trying to take small steps in the direction that you know your error is smaller. And this is also something very intuitive that you can kind of play around with in the learning notebooks. So to recap, here I've shown you like what is a simple linear regression and a multiple linear regression, and the only difference is basically just the number of coefficients. It's very, very important that you know this assumption of like no multicollinearity existing. So your features should be independent, so be careful with that. And you can, hopefully you understand that you can fit linear regressions in different ways, even though we'll probably focus more now on using like the scikit-learn closed form of linear regression, but you can also use gradient descent. So the thing that you will learn a bit more about in the next SLU, it's also applicable to this. So it's also important to keep in mind that even though it's the same problem, it can be solved in many different ways. So you are not kind of like forced to use only one method. This can be, you can even compare the 2 methods, and there's actually some part of the learning notebook for you guys to do that and see which one is better. Yeah, and tomorrow we'll learn a bit more about that also when we look into metrics. And that's it. I hope you can do all the exercises based on this. If you are struggling with some of the exercises, try to also look at the learning notebook and the examples, because we try to put a lot of things there that will directly help you in the exercises you're asked to perform. Yeah.